want chair inside so that you have a place to walk around.
Okay, we'll start. Good morning, good night, good afternoon, because this is kind of chi-square minimized time slot for Viva. And I welcome you all to this thesis defense of Vishal. And he is the first from his batch to defend. And as usual, this defense consists of presentation by the student for about 40 to 45 minutes. And during this time, unless otherwise you have a very pressing question, please don't interrupt Vishal. But this is not for the examiners. Examiners can stop him at any stage and ask him questions. Once the formal presentation is over, floor will be open to the examiners to go through their questions. After that, you will get a chance to ask questions to Vishal. Then we will conclude based on the recommendations from the examiners. Before that, there is a formality because I looked at the reports of both the examiners, and one of them, I think it is Bart. He has given several comments for you to implement, and I guess you have done all of them and formally shown it to me. Yes. Yeah. And so in case in your presentation, Vishal, if there are occasions where you have implemented those corrections, or in case you want to respond to the comments, you can do so on the spot itself till waiting for the questions. Sure. Asked in the end. Sure. Okay, without delaying any further, I will request Vishal to go with the presentation. Okay. So, everybody can hear me, right? Yes. It's audible, right? Okay. So, hello everyone and good morning. As you all know, I'm Vishal. It's a pleasure to be here and defending this thesis, and I thank you for everybody for coming here. And without further ado, let us proceed. Is this working? As you should. Yeah. So this is a list of publications that have come out of my last 4.5 years or so here at IUCAA, of which this top 6 publications are a part of my thesis, of which the top 5 are published, and this one is in preparation. So this is for your reference. And without further ado, let's move on to the sun. And this is a nice picture of the sun I took from Nainital with the Himalayas in the backdrop and the sun setting mildly there. The sun, as we all know, is basically a ball of plasma, which is being filled with a lot of magnetic field. On the left there, what you see is the photosphere of the sun, the surface from where the optical light photons become free streaming. On the right, we have the extrapolation of magnetic field lines, which show that these magnetic field lines spread all over the solar atmosphere and possibly into outer space. It is interesting that this light that we get, the various wavelengths, different wavelengths of light correspond to different properties of the solar atmosphere. And to appreciate these differences and what we learn from light, let us zoom onto the sunspot here. And if we zoom onto the sunspot and probe it in different wavelengths, we see a drastic variation in the kind of structure that one finds in these sunspots. So this variation in structure basically occurs because the light that we receive comes from very specific processes that depend on the local temperature, density, and other thermodynamic conditions. And very qualitatively, we may map the different wavelengths that we find here to different heights and different temperatures in the solar atmosphere. Peculiarly, what one may notice, or what one would notice here, is that the solar photosphere is at around 5500 Kelvin, whereas if you go higher up in the what is called the solar corona, the temperature increases to around 1,000,000 Kelvin. This peculiar rise in temperature is what is known as the coronal heating problem. Now, the solar atmosphere doesn't just stop at the corona, it just starts fixed there. What happens is it becomes free streaming as it keeps expanding outwards and it becomes a solar wind. This is basically a stream of particles propagating across the whole interplanetary medium. This solar wind can be measured. The particles in the solar wind, the properties can be measured in situ. And what we find is that the solar wind, by and large, comes in two primary modalities, called the fast wind, which is associated with these polar regions, and the slow wind, which is associated with these equatorial regions. And you may then ask that you have this myriad set of structures that's occurring all over the atmosphere of the solar wind. What sort of processes dictate the dynamics in the solar atmosphere? So for this, we use a term called plasma beta. It's a measure of, it's a ratio of gas pressure to magnetic pressure. In the photosphere and in the solar wind region, the dynamics is dominated by the gas pressure and velocity motions, plasma motions. Whereas in the corona, it is the magnetic field that dominates and dictates the dynamics of various processes that occur. But the interesting aspect is that you may have all sorts of granulation and these bubbling that's happening in the photosphere, which is dictated by gas dynamics. But this is causally connected to the dynamics that occurs higher up in the corona and all sorts of events that we see in the corona. So it's not just trivial to separate these regions individually, but rather there is a flow of mass and energy across all of these different regions. And if you look at the solar corona itself, there are three large morphological features. We have the dark coronal holes, which are basically regions with excess open magnetic flux. We have the bright active regions, which are regions with a lot of closed flux. And these two exist on top of a background called quiet sun. Now, the solar wind, both the fast wind and the slow wind, show association with these coronal holes here. Whereas the slow wind also shows association with the boundaries of active regions. So this is the background. I'm giving you background information of various things that occur in the solar atmosphere. With this background, we ask a couple of science questions. First, what is or are the underlying mechanism of heating of the solar corona? And next, we ask what is the dynamics and what are the differences in properties of these regions that we claim are probably sources of solar wind, and how do they compare with regions from where we know that significant solar wind doesn't come, and what is the physical picture that gives rise to these differences? And finally, what are the source regions of solar wind in the first place? Is there a way to quantify it in a different way, and can we forecast solar wind conditions given changing conditions on the source side, on the sun side? So these are 4 questions that we ask in this thesis and that we intend to answer in this thesis. We will take each of these questions one by one and present our results in each of these questions. So first, let us look at the coronal heating problem. To understand or to appreciate the coronal heating problem, we must also go through the tale of 2 suns. The sun exists, there is something called the solar cycle. In which the sun exists in a maximum phase for some time and a minimum phase for some time. This active sun, basically, you can see that you have all these large events that are occurring everywhere. You have these flares, active regions, and all sorts of wildly dynamic phenomena occurring everywhere. However, if you look at this very solar minimum phase with the quiet sun, you don't have these large structures, large events occurring. Rather, it looks very benign. But look at this carefully. You will see that a lot of transient activity is actually occurring during these quiet times also. So it may seem quiet when compared to this active sun, but inherently there's a lot of transient activity going on. Transient activities are interesting because they are seen to occur over a range of length scales, energy scales, and time scales in the solar atmosphere. You can have flares or active region jets which occur over length scales of hundreds of megameters. But you can also have small scale brightenings and specules, which occur in quiet sun, for example, over a range of couple of megameters to tens of megameters. So this myriad set of impulsive events occurring over such a diverse set of scales begs us if the solar atmosphere, the solar corona, may be impulsively heated or not. And that is one prior that we have in this work. To put it more precisely, what we ask is impulsive heating a viable paradigm for explaining the heating of solar corona or not? That is the question we ask. And of course, people have this plot here basically comes from a collection of a lot of literature. And what people have done is they have gone and measured the energetics of events that occur over a range of energy scales. And they find that all of these events seem to follow a power law distribution characterized by a slope alpha. But here's the thing. This is a typical Poisson light curve. Is it possible to unambiguously determine how many events are there in this light curve? Given that you have noise, you have unresolved event, like you have two events occurring very nearby, can you do that? Can the counting hypothesis actually work in these Poisson light curves? It's a bit difficult, and the unresolved nature of impulsive events in these Poisson regions makes inferring the heating properties quite difficult. And so we may not be able to exactly count individual events. So what can we do? We can actually constrain the properties of these events through statistical properties of Poisson. So we know that the Poisson intensities are known to follow a log normal distribution when taken spatially or temporally. So this points to a Markovian process in play. So a multitude of impulsive events which are related in some way can, in principle, statistically give rise to a Poisson light curve. That is the assumption here. That is the model here. And this was developed by Paul and Solanki in this model, where to generate a given light curve, what you would have is a bunch of different impulsive events. Each impulse, the frequency with which these impulsive events occur is set by the event frequency called PF. Each event lasts for a time scale, tau, and the amplitude of each event is sampled from a power law with a slope of alpha and the bounds of pi max and pi min. So these 5 parameters uniquely determine a given light curve which erupts from this model. So this is a forward model and prior we work with. So we assume that this can explain Poisson light curves. Now we need to infer these parameters given our observed light curves. So we need an inversion scheme. To invert these light curves, we have a neural network based inversion. So what we do is we generate a bank of simulations and we train a neural network on these simulations and map the light curves to these 3 parameters here. And then during inference time, we feed in the observed light curves, the same neural network, and infer these 3 parameters up. Now, if your data is well calibrated, then you may be able to also perform a small minimization over the bounds of the power law and generate constraints in the bounds of the power law too. Otherwise, you need to have a good guess for what these bounds would be in the first place. So this whole mechanism was used or was deployed on extreme ultraviolet data and X-ray data in 2 different sets of papers. And let's look at the results that arise from these two evaluations. So for the EUV data, the orange light curve in the background is the actual observation. The blue is the simulation. You see that the simulations that we infer are the best fit from the observations using the neural network. They are well explained in terms of a good match in the CDF and in the intensity histogram. So distribution-wise, they are very similar. And they have peaks at similar frequencies in the power spectrum, showing that the similar temporal scales are being important in both observation and simulation. So we perform this inversion around 300,000 light curves in 3 different passbands of AIA, and we're able to generate statistical results on what these 3 parameters are. But the thing is, there is no absolute flux calibration in this data. So we may not be able to estimate what the actual amplitude in, let's say, ergs is for these individual events. And so for this reason, we go and perform the analysis on the X-ray data, where we actually have absolute flux calibration. And similarly, our model is able to generate parameters which can explain the Poisson light curves, this time in orange, and the simulations are now in black very well. Especially if you see that the histogram and CDF match very, very well. And since we have absolute flux calibration, we're able to perform inference on all the 5 parameters. And what we can also do is we can go ahead and compare the amplitude of these events with the amplitude of microflash, which have been observed with the same instrument. So the counting statistics comes here, and we have a statistical model here. So what we find is that these events that we have are extremely small, much smaller than what these microflash are. And we estimate a radiative flux of around 10 to the 3 ergs per second per centimeter squared from these small events alone in Poisson. If we now look at, perform an analysis on how these parameters vary approximately with temperature. So this is an arrangement of the different passbands in approximate temperature scale. So on increasing temperature from right to left, we find that the events tend to become more transient because the time scale reduces, and the alpha reduces from more than 2 to less than 2. It seems to indicate a change in the kind of dynamics that occurs. Similarly, the event frequency is inversely related to the average amplitude of individual flares, both in UV and X-ray, which tells us that there is this possibly an energy reservoir which is being depleted by large events occurring intermittently or small events occurring very frequently. So, impulsive heating seems to, at some level, be a viable mechanism for explaining quiescent intensities. Now, let's move on to what the differences between quiescent regions, which we know are not significantly contribute to solar wind, and coronal hole regions, which we know are well associated with solar wind. So we have seen this picture earlier in some measure that the coronal holes and quiescent have this stark intensity contrast in the corona. But if we approximately probe them at lower and lower temperatures and lower and lower heights, we find that this intensity difference or intensity contrast seem to visually vanish. Doesn't seem to exist here anymore. So lower in the atmosphere, you don't have these intensity differences, but higher up in the atmosphere, you get these stark differences. Why would you get this differentiation in the first place? So this understanding why this differentiation and how this differentiation occurs would be the key to understanding how the solar wind actually comes from the coronal holes, and even possibly understanding how the quiescent is heated up. People have worked on this topic already, and these figures here are from Don Hassler et al.'s papers. So on the right, you have the coronal holes here. So the coronal, these images, or these are from the upper tension region neon 8 line, wherein you see these intensity differences between coronal holes here, the quiescent here. You also see that there is an excess outflow coming out of the coronal holes compared to quiescent. What Don Hassler and others also found was that these excess blue shifts, for example, were very much concentrated on these depth of region boundaries, which are regions, these black lines, which are regions with very strong magnetic field. And they also found that the excess intensities are not concurrent with the excess blue shifts that they find. So possibly they hypothesized that the energy dumping mechanism is either driving flows in one context or either locally heating plasma in another context. Another paper by Tu and others, they look at just the coronal holes alone, and they find that the solar wind actually emerges out in these funnel-like structures and it's propagated outwards. So solar wind actually emerges, comes out in coronal funnels, is what they say. So how do we explain the differences in these intensities? So one possible explanation was provided by Riegelmann and Solanki, where this is the EV data of a coronal hole, and this is magnetic field extrapolation of the same region. And what they find is that the coronal holes and quiescent regions have approximately similar number of short loops. But then, if you look at the longer loops, so this is loop length, and that's quiescent, this is coronal hole. And the longer loops are kind of missing in coronal holes, but they're present in quiescent. And typically, your loop length scales at temperature. And so in higher pass bands, you would actually find these long loops which are giving out any emission, whereas the short loops are present in similar number. So you see visually similar kind of signatures in coronal holes and quiescent. So at lower atmosphere, there seem to be some confusion. So we asked, what happens lower in the atmosphere? And for this purpose, we use rasters from IRIS. And these are 3 different spectral lines we studied: magnesium line, carbon line, silicon line. And make note that the magnesium line intensities were studied by Pradeep Kashyap and collaborators, and we have expanded all of this in this work. So this is a typical set of plots of silicon, carbon, and magnesium. You can see that the magnesium line looks very beautiful. It has these 2 peaks and a dip there. So that dip is the line core, and these are the line peaks that we have. Typically, in these conditions, silicon forms in optically thin conditions, whereas carbon and magnesium form in optically thick conditions. But make note that carbon too can also have an optically thin component that may have an influence on these different results. Now, what we can do again is we may qualitatively assume that these different spectral lines probe very specific layers of the atmosphere and arrange them by height. So basically, we are looking at the temperature where these different spectral lines form, and we are associating that temperature with the height. But this is very, very qualitative. But then it serves a purpose that the silicon line generally tends to form much higher than the carbon 2 and the core of magnesium line, whereas the peaks of the magnesium line tend to form much lower in the chromosphere. So with these bunch of different spectral lines and features, we are able to probe from the chromosphere to the lower transition region in a large range of the atmosphere. The silicon-4 line was studied by Durgesh and collaborators, and we have expanded in this work. Whereas the carbon line, the magnesium line, the synergy between all of these lines is studied in these two papers. So what we do is we take the intensities, velocities, line widths, and all of these quantities, and look at the variation as a function of the underlying photospheric magnetic flux density. So what we have the first plot here is the intensity ratio between quiet sun and coronal hole. The black is the chromosphere, the orange or yellow is the transition region. We find that already in the chromosphere, the intensity is obviously increased with magnetic field, but then the quiet sun intensities are much larger than the coronal hole intensities already in the chromosphere. While visually you don't see the difference, if you build in magnetic field, you actually see the differences. And this ratio is smaller in the chromosphere, but larger in the transition region. That's an interesting result we already have. And then we find that if you look at the average velocities in these two regions, in the chromosphere, quiet sun and coronal holes shows consistent average velocities, whereas in the transition region, the quiet sun is more redshifted than coronal holes. And then we study the properties of blue shifted and red shifted pixels separately, because the magnetic field can have preferential action on these two kinds of pixels. And we find that in the chromosphere, this is the difference in the blue shifts in coronal holes and quiet sun. We find that the chromosphere itself, the coronal holes show excess blue shifts compared to quiet sun. And this excess is not as large, but in the transition region, this excess blue shift increases. So we see signatures of these blue shifts already, which were seen in the neon 8 line very clearly without these differences. We see them statistically if we bin in the magnetic field, in the magnetic flux density. And finally, if you look at the redshifted pixels, in the transition region, we find that the silicon-4 line, shows excess redshifts in quiet sun. But then in the chromosphere, it is the coronal holes which show excess redshifts and not the quiet sun. So there seems to be a dichotomy that's occurring here. So everywhere else, there was a kind of an order being followed. And here things are getting thrown out. So what is this dichotomy? How do we study it? To study this more, what we do is we perform cross correlations between velocities in the chromosphere and velocities in the transition region. And what we find is we look at the downflows that are occurring from the transition region to the chromosphere. These downflows are very tightly correlated. So whatever plasma is flowing down from the transition region is flowing down in the chromosphere. And the downflows are decelerated much faster, are decelerated much more in quiet sun when compared to coronal holes. Same is the case, or rather, similar is the case with outflows. Outflows are accelerated. Outflows in chromosphere are accelerated into the transition region. And we find that the coronal holes now show excess acceleration of these outflows when compared to quiet sun. Then if you look at diverging flows, we again find these diverging flows are correlated. And these outflows, which are occurring in the transition region, are stronger in coronal holes when compared to quiet sun. And finally, if you look, so this is a typical case of a bidirectional flow. And finally, if you look at converging flows, we don't see any relation whatsoever. So to explain these correlations can at some level be explained by one mechanism such as this. So if we have an impulsive event which occurs in a column of atmosphere, that would make the plasma expand in both directions, giving rise to bidirectional flows. If such an impulsive event were to occur much lower in the atmosphere, it would drive the plasma flows outwards if the resistance in the atmosphere is stratified and if you have a mass flux conserving flow. If this impulsive event were to occur at the lower transition region, at the base of transition region, you would have bidirectional flows with outflows in transition region and downflows in these chromospheric lines. But then note that not all the plasma may just escape. Some of it can also fall back down. And as it comes back down, you may see correlated flows in all of these different lines. And finally, you may have impulsive events that occur very high in the corona that can drive downflows across all of these different lines. Note that this is just a qualitative picture. It's one of the pictures that can explain this phenomenon. But the solar atmosphere is far more complicated. You have all sorts of events going on. You have shocks that are randomly causing things in the atmosphere. You have slightly different properties occurring in the strong magnetic field and weak magnetic field regime. You have what are called spicules, which are basically jets of plasma that sort of pulled up by tension forces or even by flux cancellation or various mechanisms. So this is one picture that can possibly explain the velocity correlations that we have. And if we combine this with the loop statistics picture that we obtain to explain the intensity correlations, what we get is a picture like this. We have basically in the quiet sun closed loop, the underlying process that basically drives quiet sun heating and solar wind motion in the coronal holes is basically magnetic reconnection. Reconnection in the form of closed loop reconnection, closed loop reconnection in the quiet sun locally heats the plasma. The plasma can't escape, just fills the loop, and you get this excess, this high brightness. Whereas in the coronal holes, it is interchange reconnection, which dumps the mass into these open tail lines, and plasma is just taken outwards into the solar wind. And if this interchange reconnection occurs much higher in the atmosphere, possibly they can give rise to what are called these switchback structures also. So this is the kind of picture that we envision coming from the observations that we have. So basically, the heating of the solar corona and the emergence of the solar wind are possibly arising from the same underlying process. It is just that they occur in very different environments. So, and now we have been performing 2.5D simulations, MHD simulations in different magnetic field of background topologies. This flux emergence in these two different topologies qualitatively have some form of results that we are seeing in these observations. But what we need to perform is to perform spot modeling of the spectral lines and see if they're actually encoded in the spectral lines that we observe. And with this, let's move on to the last question asked in this thesis on the sources of solar wind. So we have been looking at sun-side relations, right? We have been looking at what's happening on the sun and the thing that's coming out of the sun. We flip the whole problem here. We try to focus solar wind properties given changing conditions on sun, and then query the model to understand which regions of the sun are important for this kind of forecast. So that is going to provide us a very different constraint or a very independent constraint of what different mechanisms have done till now. And this is published in this paper in Space Weather. So if we are to phrase the problem appropriately, we basically want to translate a sequence of solar image measurements into solar wind measurements. So think of this as translating one language to another language, right? It's basically the way we all think. We are speaking in one language. I'm thinking in Hindi and Tamil, I'm speaking to in English. So that's what is happening here. Except these are images. It's an image time series here. It's a wind time series. So what we have is we have a feature extractor which encodes this each image into a vector. So we have a time series of vectors, which is then regressed with the neural network to a wind speed, to make the problem simple. This whole neural network is what we call WindNet. And we have around 8 years of data with one forecast per day. This whole scheme lets us forecast the solar wind speed 3 days before it has even come to Earth. It is able to capture all of these transient enhancements that occur in the solar wind. And since we know that the model performs reasonably well, we can then probe the model with interpretable AI methods, as they are called, and see which regions of the sun are actually important for a given modality of solar wind. So we had seen earlier that the slow wind is associated with the active region boundaries, and the fast wind is and slow wind is also associated with coronal holes, whereas the fast wind is predominantly associated with the coronal holes. So we can actually ask for the fast wind, what regions of the sun are important for this model? Let's see what it says. So this is a fast wind forecast, and what the model says is the coronal holes are actually important 4 days before prediction for this fast wind, and that is really entirely similar to the physics that we know, that this fast wind would take around 2 to 4 days, or around 4 days or so, to come to Earth and for other measurements. So this was very interesting for us. And what we do is we then go and look at we probe the slow wind regime. The model tells us that the active regions are now important for the slow wind forecast, and this is like around 7 days before prediction. Whereas there is some increase in activation around in the coronal holes much closer to the day of prediction. This again is well known from physics, or rather well known from the physics, but we didn't feed any of the equations of prior physics to this model, and this is just a mapping that the model has learned from this data-driven analysis. But what we just do is we just don't stop here. What we rather want is some form of statistical result across the whole data set. If we consider the whole data set, what does the model think? Where does the model look at for slow wind? Where does the model look at for fast wind? That's what we want to understand. So if we take in the whole data set, the diamonds correspond to the activations in the coronal holes. The dots correspond to the activations in the active regions. What we find is that statistically, across the whole data set, the coronal holes show enhanced activation 4 days before prediction. And this is a very strong result. And this is consistent with physics. Interestingly, we also find that the active regions are also deemed important for this fast spin prediction, but this is 5 days before prediction. And that is something that needs study. If you look at the slow wind, the model thinks that the active regions are now very important for slow wind prediction. But then what happens is that this temporal sequence is not what we know from physics. Slow wind is supposed to take time to come to Earth, whereas this thing says it's 3 days before prediction is what it deems important. So it's possible that some of these active regions, at least in the data set that we have, they last for a long time. So possibly the model gets confused as to which sequence it wants to look, because you already have signatures of these active regions in the temporal stamp much closer to the day of prediction, and it just uses that. It's a hypothesis though, but the whole point behind this analysis is that this physics is in some measure being captured by such machine learning methods and deep learning methods. And it would be extremely important and interesting to probe how this physics is captured by these methods like GradCam. And GradCam is just the starting point, right? This has been done a long time ago, and now things are expanded to a lot of different feature attribution methods which people are using in science. So, what are the key takeaways from this thesis? The first thing is impulsive heating is indeed a viable source of heating the quiet corona, and it may also possibly be a unifying paradigm for quiet sun heating, for solar wind emergence, and for generation of stick flags. And this is possible in the form of interchange reconnection in coronal holes and quiet sun and closed loop reconnection in quiet sun. Our observations also suggest that already in the lower atmosphere, we see signatures of solar wind forming, and these signatures are seen only if the underlying magnetic density is taken into account. And finally, the morphological features in the corona show an association with features in the solar wind, and these can be captured and probed by using deep learning and interpretable AI methods. So, future outlook. So many paths have emerged out of this thesis. There are many projects that have spawned, many clarifications that came from this thesis. So one of the first things that I want to look at is to constrain statistically the various heating mechanisms in solar corona. And this is possible with high throughput instruments that are coming up in the future, like MUSE and UVST. Next, these instruments not just look at the heating aspect of the solar atmosphere, but also would go synergistically with other instruments through which we can probe the flows across the whole of solar atmosphere, and we may attempt to constrain the momentum energy transport in the solar atmosphere itself. We would like to localize the sources of solar wind, not just spatially that we have seen in the previous project, but we would like to also do this localization in temperature. So if we take multi-thermal data instead of just one passband of data, then we can also generate these GradCam results across all of these different passbands. And that is something we are working on right now. Some project going on right now. Furthermore, the solar wind that we receive here on Earth or wherever or near L1 that is measured, this solar wind is actually processed as it comes from sun to the Earth. And this processing is something that can be thought of as an information loss problem. So we have an amount of information that is being lost and it's coming to the Earth. And it would be interesting to study this whole problem using the future instruments like SOOT and AI. So the synergy of SOOT, AI, and EAC. If you see, for example, plasma traveling outputs, and with in situ instruments for plasma that's traveling to the left side. And finally, we have the forward modeling. We have the simulation going on, where we are seeing a lot of quantitative risk agreement between what's happening in the simulations and some of the observations. And we would like to take it further and forward model spectral lines and see if the spectral response is actually similar, or if it's and see what happens there basically. So these are a couple of projects, a couple of ideas, a couple of paths that have emerged out of my thesis. And with that, I would like to thank my guide Virgesh, my mentors, my collaborators, and of course my IUCAA family here. So thank you.
Thank you all for inviting me. So Anand had to teach, so he left and he asked me to conduct this. So as is the custom here, we will have the questions and suggestions from the examiner.
We can do some. I don't know if that.
Okay, so both the examiners are there.
Yeah. Yes.
So we'll have the questions from Professor Louise Harra. So Professor Harra, can you ask the questions?
So thank you, Fishel, for a really nice thesis and presentation, first of all. In your discussion on the impulsive events in the quiet sun, you use particular filters in the EUV. What do you think would happen if you used different filters, if you went down to the cooler filters, etc.? Would you see the same thing everywhere?
That's a good question. I mean, people have seen, if I remember correctly, I think David, Jess, and others have a different set of methods. It's not the similar kind of, it's not the same kind of paradigm that they operate in, but they also look at some measure of intensity distribution, and they do see impulsively heated atmosphere lower in the chromosphere, if I'm not wrong. We have that relation to go far back. But we didn't see this relation occurring between, let me go back on the, in this emphasis, yeah. So we didn't see this, this is a very approximate average relation, right? Because you have a distribution of points occurring everywhere. But as the temperature reduces, the time scales seem to increase, the alpha also seems to increase. So I'm guessing that in lower end atmosphere, in cooler pass bands, this would hold and the time scales would be much longer for these different events. But yeah, this is something that we need to probe to give a decisive answer. Yeah.
Do you have any concerns about using imaging data for this when the filters are quite broad, that the temperature is maybe not so accurate?
That is true. Yeah, it would be best to actually look at spectral data and high cadence rasters like like news. But we possibly work with what we have. So.
Yeah. I mean, you could try and use some sit and stare observations in the spectral data.
Yes.
Might be quite interesting to do similar work with that.
Yes.
And you had when you use your plots of the simulations and the data, I can't remember which slide it is now. It's close to this one. I think it's
this is
further back. I think it's further back, actually.
This one?
Yeah, this one. One of these. So you've got your simulations and your histograms. When you compared your histograms, they're quite comparable between the simulations and the data, but you get quite a difference in the peaks, the small peaks, as you mentioned.
Yes.
And that's a very hard thing to get right. But if you looked at a patch of quiet sun, what do you think would be needed to predict exactly when you're getting impulsive events, when they're going to happen? So if you look at, I think the previous, in the EUV, it's maybe more obvious in the previous one. So you get sequences of events where the background is higher and then you're getting multiple peaks on top and then it lowers down. So what would you think you would need to get those peaks overlying each other, which I know is incredibly difficult to achieve?
So one of the ways in which I think these peaks overlay is you have events occurring over the same pixel, that you're not resolving these events spatially. What we are seeing is just an average over a small region. And that can, in principle, give rise to an event is occurring in let's say there are 2 pixels and you're just average over these 2 pixels. And that's possibly how we would see that we have 2 events occurring over each other. Because if you look at, for example, I can show you this plot. So you can look at these time step at 25. You have these 2 events occurring very close in time. But one event is small, the other event is kind of larger than that. And the signature of the smaller event is round in the signal of the larger event. So spatially, this can happen. Temporally also, if for whatever reason you had a small event first, a much larger event occurring very close in time, and we didn't have the time cadence to capture that. Yeah. These signals would get round. That is how I'm envisioning it.
So your kind of dream instrument, what time cadence would you want?
So that is a very good question, because temporally, I am not very well aware of what would be the shortest time scale over which you can get two events. I'm not sure as to what would decide that kind of a time scale. So the more the better is what I would say. But giving an exact number, at least in cases such as these, would be very difficult since we don't have such constraints.
Yeah, so it is difficult, and it's always the better cadence we get, the more we see. So,
Yes.
When you used your X-ray data, you were using sun as a star data, and how difficult is that to compare to the EUV data when it's quite a different way of observing?
Yes. So sun as a star data would actually be averaging over multiple such events occurring all over space. So, I mean, since this is all statistical, so the log normality exists if we take the distributions either spatially or temporally. So that is what is driving us to make some qualitative comparison between X-ray and EUV. But you are correct in the sense that X-ray emission in the quiet sun from the quiet sun is not as large as, for example, 171 emission from quiet sun, right? So very small events can actually just get averaged with the noise. Since we do have noise here, in this field light cause noise incorporated, and they may just get drowned in noise. So there may already be underestimation of events going on in the X-ray regime. So while we can compare to some extent qualitatively the results here with the EUV results, but the quantitative comparison is not something I would at least recommend.
Did you?
Yeah.
Sorry, Vishal, go ahead.
Yeah, simply because of the averaging effect. I mean, the small events must just very small events can just be killed off within the noise.
So do you think you would get similar results in X-rays if you used XRT, for example, on Hinode?
I would like to have a look at that. I can't, I've not looked at the exact data actually. So if I look at it, and I don't particularly see, so generally I see all of these much brighter brightnings or microflares that are seen in XRT. I have not seen, so the quiet sun results generally were seen by Tasukawa and Sylvester and other people. So I did read a couple of papers from there, but they're all individual events that were resolved. But analysis like this, where you just have the time series, you don't see any strong events, is something I would have to look at first.
The 2-on-1 angstrom result would be similar to what XRT would see by and large.
That is true. The 2-1-1, yeah, 2-1-1 could be a good proxy for what XRT would see. Yeah, the softest filter XRT, exactly, for example. Yeah.
So just in another, going to your work with ARIS, which was really nice work that you did. One thing I wanted to ask was your carbon-2 profiles. So the carbon-2 data doesn't look so statistically good, but you measured a negative skew in that. So do you think that's really accurate?
So that's a good question. We do the carbon-2 data is not as good as the magnesium data, that's for sure. I mean, I agree with the statement. But then the skew measurements, if you actually look at the whole plot, there is only a mild variation in the skew itself, but the skew values are much different from a Gaussian, and that's exactly what we want. The Gaussian fit. So what we're comparing is the Gaussian fit with the profile itself, and there is a marked difference between the Gaussian fit and the profile. So that is a major result we are looking at. Whereas the variation in the skew and the kurtosis also is there is a large error bar there. That is true. And we need to average, that is also true that we need to average over multiple pixels to get a very good signal in the carbon-2 profile. Yes. And there may be, wherever the intensity is more, the averaging is not as strong, but in regions with low intensity, this effect is pretty predominant. And I don't remember exactly which pixel was this, where you have this kind of a thing. But you can see that the profile actually exists quite well in this light curve that is shown here.
Okay. You do talk in your discussion. You mentioned the argument between type 2 spicules and waves, and that's an ongoing debate in the community. But would would you be able to say how you can clearly distinguish between those observationally?
As the elephant in the room.
It's really difficult.
Yeah, yeah. So yeah, that's true. That's a very appropriate question. So type 2 spicules. So the reason why we are a bit more inclined towards the deconnection based process is simply because the type 2 spicule velocities are far more larger than what we measure, but the effect of the background which spicules give, and on top of that you have all of these events going on. That is not something that has been simulated. Yeah. So the simulations that we that have been performed by simulations, they don't incorporate the effect of spicules. So we don't know the effect. We don't know the comprehensive effect on the spectral lines that form, and how the correlations between various parameters may change. So yeah, so unless we measure these things, measure these phenomena directly, we may not be able to get any constraints here right now. But correlated flows is a very interesting and I think an important driver for differentiator between the spicule case and the impulsive event case. So,
okay.
Yeah.
Another question that so the community doesn't know the answer to necessarily, but I'm curious what your opinion is. So you mentioned magnetic switchbacks in different places, and related your work to those. Now switchbacks, there's multiple theories being put forward for switchbacks where they can form low down or higher up, etc. And they come in bursts and they behave differently if it's coronal hole or quiet sun or active region. How would you explain those differences in the behaviors of switchbacks and the basis of the theories that have been put forward? Do you have a preferred theory that's been put forward?
Well, I try to work with no preferred theories because that kind of then biases what I want to see in what I see in my data, because we tend to find patterns which match, which confirm our biases. But one way to differentiate switchbacks which form, let's say, between coronal hole boundaries and quiet sun and open flux and active regions would be to look at the composition, because I'm guessing the composition, because let's say the slow wind composition is different from the fast wind composition. So I'm assuming that the composition in switchbacks which come from these two regions would also be different. Now, if the switchbacks are forming in situ, switchbacks forming in situ and switchbacks forming, let's say, lower down in the solar atmosphere, we did have these couple of papers, Fargate and others, where I think even you were there in those papers, where the wavelet power spectrum and the typical length scales of the duration of switchbacks, they conform to supergranulation scales. And it seems that if you want to relate the duration of a switchback to supergranulation scale, there must be a causal connection between what's happening in the sun, on the sun, and what's we are measuring in situ. So there is a strong prior there, but then you do have the distribution of the time scales and duration of switchbacks, which probably point towards a more in situ formation. For example, the papers by Jonathan Square and others. So composition, I think, would be a very important differentiator and demarcator for where switchbacks may form.
Yeah, I think that's also quite a difficult measurement, because you don't have that measurement in Parker Solar Probe, but you do in Solar Orbiter. So it's kind of connecting those two up. Also, when you're going from very small scales and super granular scales into the solar wind, I think connecting those scales is also extremely difficult. He also talked about the importance of active regions in the slow wind, and the images that you showed there in your data, they all had active regions, but in the case where you have no active regions on the disk, what would you expect to see? So the active regions, when they're there, they obviously contribute to the slow solar wind, but when they're not there, then what would you expect?
That's a good question. there are always some form of transient brightening. So I'm expecting that the machine would pick up these brightenings. But I have not actually gone and checked. I don't know why I didn't check this, but I should have actually gone and checked this thing. If there are no active regions or no coronal holes, which is rarely the case. If you're not having any active regions, possibly it's solar minimum, so you would have some coronal holes that would be picked up by the model. But if you don't have either of those two, the model would pick up small scale brightnings or brightnings of some sort, which do exist all the time in the corona. So
yeah, I think it would be really, it was something that really leapt out when I read it, because I think it would be really interesting to see, because you being able to use EUV images to infer solar wind sources is super interesting that this works so well. But if you can kind of look at it in situations, extreme situations, if you like, of when the sun is extremely quiet, what it picks out as being important would be interesting, because then you would need to understand what is being fed into the streamer belt and so on. So that could be really interesting.
That is true, and also that this model, when it was formulated, there was no research per se in the machine learning community of capturing the uncertainty that would come with the forecast, right? So I'm giving you some forecast numbers, some forecast velocity here. I'm not telling you what the error bar on that forecast is. So now there exist methods where I can tell you that the wind speed is so much and there's an error of so much, so the uncertainty of so much, simply because the model is confused with the input. So if we are to train with that sort of a mindset, I'm guessing that such a image would typically make sure the uncertainty which the machine generates would be quite large, because you don't have a very strong signature of risk from the active regions or from the coronal holes. But if the machine gives a very low uncertainty forecast, that would be very interesting to look at, because then it is more confident of the regions that it is probing on the disk of the sun, in the solar atmosphere. Sorry.
Yeah. So when you did your summary at the end about the future work you want to do, you had a really nice list of topics that you want to do, and I'm showing my real bias here, but you didn't put in how you would use solar orbiter or Parker solar probe here with all your topics in solar wind. So I was wondering how you would make use of those.
Oh, it's okay, yeah. So it's a brain fade. It's supposed to be here in the evolution of solar wind, because as the solar wind comes from the sun to Earth, and you have these various in-situ measurements occurring all the way to the sun, that is going to constrain it's going to give like really good constraints on how much information is being lost as structures arise from the sun and come to the Earth. So yes, it was supposed to be there. I just forgot to put this item. But it's PSP and solar are here. Yes, they're certainly here. And this localizing in source regions, it's something we will be looking at PSP data soon, but we're not got into that yet.
Yeah, excellent. Okay, thank you very much, Vishal. Thank you.
Thank you, Professor Harra. So may I now request Dr. Pontieu to ask questions?
Yeah, hi, Vishal. Very nice work. Very impressive, all the different topics and skills that you've covered here. So I had a couple of questions, and thank you for addressing the comments that I had sent in. If you go back to the episodic events work, you didn't actually show this on the slide, but at some point in your thesis, you describe how you try to deal with the noise and make sure that you have enough signal to noise in your signal. And I guess for computational reasons or limitations in the computational powers that you have, you do a knee analysis and you find an optimum value for kind of the boxcar averaging in time. I guess what I was wondering about, given that the sun in the EUV has a very large dynamic range, and some very faint regions and some very strong and bright regions, we know that the noise properties, the photon noise, depends on the brightness. What I guess I'm wondering about is, given that you've had to choose a single kind of averaging window, to what extent do you think your results are impacted by that choice? And to what extent do you think your method is fitting, in some sense, the noise as well on the fainter regions?
That's a good question. So when we optimize for the boxcar window, we looked at a bunch of different light curves, and by and large, we found them to be consistent around a window size of 5, and that's why we went ahead with 5. But what you're saying is correct, that there may be pathological cases where there is very large intensities or very small intensities. But by and large, the quiets and intensities are of similar dynamic range. They don't span a great dynamic range, except for some pathological cases here and there. So I am assuming that since this is a statistical work over like 300,000 light curves that we have, among those 300,000 light curves, mostly the light curves would correspond to cases where the dynamic range is not varying too much, and the results by and large hold. Of course, there would be cases, or there might be cases where you have very, so let's say you have a brightening of some sort. Then there are some cases where there are some bright pixels or some very dark pixels somewhere. That may cause issues, but they would be very small in number. At least visually, when we looked at the video of the 2 data sets, such cases were very small in number. But I don't have a number at hand to give you.
Okay. You also talked a little bit about discontinuities in your time series. I was wondering if you can comment on what, I don't know how many discontinuities you have in your time series, but you essentially stitch the data together if there's a time gap.
Yes.
Can you talk a little bit about what kind of artifacts that could introduce into your analysis, and what do you think that's significant?
So if we just look at it event-wise statistically, if the assumption here is that similar kind of statistical events occur all the time on the quiet corona. So in that perspective, looking at different time series, discrete time series in different times doesn't really cause a great effect. But then we do have events occurring all the time, because of which a rise or a fall of an event, let's say, can simply be cut off because of such gaps in the data. Now, there are not many gaps in the data. By and large, the data is, the data set is continuous. There are, I think, 2 or 3 cases where there are data gaps because of some eclipses. But we estimate that the effect of these data gaps is not a lot, simply because we are looking at this whole light curve statistically and not as individual events. So if we lose one event, that would still be fine. It would be better than interpolating between 2 light curves, let's say, because then that is going to reduce a lot of artifacts with a prior on what sort of interpolation would go into going from one intensity to the other. So it's rather good to lose a couple of events than introduce more artifacts with an interpolation of some sort. So that would that's why we went ahead and just contaminated the data in the series.
Okay, no, that makes sense. I guess another question is, can you comment on, so you're interpreting essentially intensity changes here as a result of heating events. There may be other mechanisms that lead to intensity changes, compressive waves, or that don't actually lead to heating. Can you talk a little bit about that and how that could impact your results?
So right now, I mean, in this model, this model is actually agnostic to the exact physical process that would give rise, that is going behind, but rather it only depends, it only assumes that the intensity change is impulsive, right? So this could occur due to nanoflares, or due to impulsive, due to waves, compression of waves, or even let's say some effect of specules. Maybe there are some effect of specules, I don't know. But it could be due to any process that is transferring energy and making plasma emit in these plasmas. It just needs to be impulsive. That's the only assumption here. So we don't constrain, or rather we can't constrain the exact physical process, which is a subset of the impulsive processes through this scheme. That is true. So I can't differentiate. I mean, the time scales, yeah. There is one thing we can do is that these time scales are much longer. So the time scale of each event is much longer than the time between 2 events, at least in the X-ray case here. So this frequency, we have like around 30 events per minute. That's like around 2 seconds per event between 2 events or something. Whereas the time scale is around 11 minutes. So these events last long, and they are occurring very, very frequently. So that may provide some constraint on the kind of underlying process that is impulsively giving rise to its intensities. But yeah, that is.
But you are in your interpretation, you are interpreting these events as signatures of heating. And I guess what I was alluding to is that some of these mechanisms may lead to intensity changes, but not necessarily be a significant contributor to heating. Does that make sense?
Oh, well, yes. Okay. Oh, now I get it. Okay. It is true that they may just be intensity changes and not heating events. And yeah. So I don't think we can disentangle these two different cases, at least in this scenario. Yeah, I agree with your statement. Yeah, we can't disentangle these two cases.
Could you imagine using other wavelengths to that are sensitive to other temperatures to help constrain that, or is that? I'm just thinking out loud here. But
no, yeah. So the thing is, we can look at multiple wavelengths for the same time frame for the same region, let's say, and we may be able to constrain whether there's a heating event actually going on with cooling or so. The thing is, these are all with a statistical model. If you want to use something like the time lapse, which were compared by Nicholas and others, so that would not be possible here because we are only looking at a statistical match in observations and simulations. So with this forward model, since it operates only on one wavelength band, I don't expect to generate very strong constraints on differences between heating and just enhancements in intensity. Because if it's heating or cooling, let's say, we would expect somehow correlation across different pass bands. And I would need to go and check on what sort of statistical measures. So we could look at, let's say, the cross correlation of light curves, for instance, but that is not going to give you enough signal, for instance, because these events are they just occur too frequently, and the signature of individual events is just going to go out, right? Yes.
Right.
So
Yeah. No, that makes sense. Yeah.
And also that this data set, this X-ray data set is quite it's full disk integrated. So again, we will be having all sorts of processes, but we can't disentangle
right
into heating with yeah.
Yeah, thank you. That makes sense. I also had a question about the iris work, the correlations between the various lines, which I think from an analysis perspective is very impressive. I guess, and I think we've talked about this in the past. I'm always struck by how relatively small the velocity differences are. Maybe you can show me the cartoon that you have. No, the cartoon. Yeah. No. Yeah. Maybe that one. Yeah.
This one?
Or this one. Yeah. Either one of these. Yeah. Okay. So the red explosions there, I'm guessing are, is a cartoon for a reconnection event of some kind, right?
Yes. Yes.
Yeah. So if you go in that direction of a reconnection event, and you've also done numerical simulations of flux emergence where reconnection happens as well, and there's been other work done on these kinds of events. The flows in the chromosphere and the transition region, that the bidirectional flows that come out of these are relatively large, right? They're of the order alphanic speeds, let's say tens of kilometers per second potentially. So can you just comment on the fact that if you now go back to your scatter plots and yeah, that the differences between the upflows and the downflows are very modest compared to those velocities. Can you comment on how you would explain that in that cartoon model that you have?
So by and large, the chromosphere. So if you look at the average velocities, let's say in quite some holes, the chromosphere, they are quite a kind of consistent, and the differentiation that we are reporting here, it is just a distribution. And you may also remember that what we are reporting here is the mean value with the standard error on the mean itself. And what happens is here this distribution of samples, and if you just look at them as for each bin here, let's say you look at two distributions and compare these two distributions. These distributions are slowly diverging out. They're not like separated out, so you don't see very large signatures. There's still an overlap between these two distributions. Now, but one idea or one explanation is that the structures in the chromosphere are still differentiating, but not extremely different. And then there could be a lot of line-of-sight effects that are happening, whereby we are only measuring a component of these flows and not the actual flow values themselves. So these could, in principle, be the reason why the differences in the velocities that we see are not large, but are quite modest and small.
Okay, so that's a very good or interesting hypothesis. Can you think of an observational method or an analysis of observations that could, support or reject that hypothesis?
That's a very good question. So what the straightforward way would be to track a given region of a Conway hole coincident boundary, for example, and over the disk, let's say. But then these flows or these events would possibly last for much shorter time, and so the signatures of these events, so they may not be just quasi-static, there's no just flowing down. But then, yeah, so let's see. If you're able to trace these flows across the whole of atmosphere, maybe with, I don't know if mules will be able to see Conway holes or not, but if we can, if we get like, we're able to get a very dense raster, instead of rasters evolving very fast over time, we may be able to constrain if the line-of-sight effects is what is causing this kind of difference, or if it's something very different, if it's this hypothesis fails. So
yeah, no, I think that's a good idea. Now, one other thing that perhaps might be possible, I just wanted to see what your thoughts are on this, is if you looked at, I mean, you have signaling here that seems to be revealing a difference, right? Or is clearly revealing a difference, even though there is, as you said, very large scatter on this. In your hypothesis, you're suggesting that that's essentially caused by outlying events that have strong bidirectional flows. Can you think of a way to look for those kinds of types of events in the spectra that we have currently, rather than in the iris data? In other words, would it be feasible to go look for those outliers and actually, because here you've got a statistical approach, but underlying that statistical approach, you're essentially non-linearly averaging over the large field of view that we have in the time series. If it is really caused by strong outlying events with strong flows, can you think of any way to go and detect those?
We would need a much higher spatial resolution for starters. Line-of-sight flows will be, so I'm just trying to look at what sort of observations we can do. So often observations can't be done because line-of-sight effect goes away. You can't measure the velocities there. On disk, exactly near the disk center, if we are to measure flows across various spectral lines, and if we, so okay, this is quite ambitious. Maybe if there's a campaign of observing very specific Cornell funnels, let's say, then look at possibly brightenings that are happening inside the Cornell holes, then we may be able to generate some form of constraint on whether this hypothesis works out or not. It's a possibility, because if the brightenings are occurring in Cornell holes, we may be able to they should not be very large brightenings also, or they may the properties of the flows and the topology that we get could change depending on how big the brightening is. So for small brightenings that occur in Cornell holes, maybe multiple such brightenings occurring very near the disk center, then possibly that can provide some constraint on whether these occur due to bidirectional flows. These bidirectional flows are what are displaced, the velocities are not. But that would it would still be a leap of faith to move on to the statistical result that we see here, right?
Right. Okay, no, that makes sense. Okay, and then I had some questions on your very interesting work on the solar wind speed. Well, I guess the main question I had is if you, and maybe you've discussed this, but when you see your signal for the slow wind and you show the fact that it's correlated with the active regions, does your method allow you to determine which of the active regions dominates? And I guess the background to my question is it just the presence of the active region that is kind of like switching on or off, whether it's slow or fast wind? Or is it something about the active region? Are there differences between active regions? Does it depend on the number of active regions? You know, these kinds of studies, and maybe these are encapsulated in your future work. I'm not sure, but I'm very curious about.
So I think,
you know, in some sense, it's surprising that these signals are there, right? I mean, are they actually really happening in that active region? Are they much higher, but connected somehow to the active region? Those are kind of the underlying questions of this.
So one thing is this is just one wavelength of data, right? So so we work with just 1 and 3 in this example here. I have not looked at whether it is due to the number of active regions, because we have just looked at the average activation per unit active region area. So we didn't really look at whether the correlation also exists between the number of active regions or not. So that is not something I can answer right now, but I could have a look at it because we have the data, we have the models and all. The second thing here is differentiating properties of active regions, at least in the case like RADCAM, and this paper, as you know, came out like 3 years back. It's not very well advised, because if you see, all of these structures are very, very blurry. And that's because RADCAM is itself quite an approximate method for inferring what's going on in neural network. So it will not give you all of these edges and high frequency structures that you see in an image. It will only give you more of, it would give you more of the low frequency structures, right? So it is rather ill-advised to actually go and perform such an analysis on something like RADCAM. But then we have other methods that have come up in the last couple of years. And these methods, at least I'm seeing the current analysis I'm doing, that it is actually able to, at some level, trace out even the loops present in near the active regions. So of course, the model training and everything, this is the big it. You need to have a very well-trained model. But in this new kind of a setup with better activation visualization methods, we can actually look at, whether it is specific properties of the active region that's driving slow wind, or whether it's the number of active regions in a given image that's driving the slow wind, or if it's something very different. And in the new analysis, we are actually having multi-wavelength data. So that is going to give us far more information on the properties of active region sensors. So yes, that's a very interesting question, and we are looking at it. I'm just giving you things that are in progress. I'm not giving you answers.
Right. Yeah. No, that makes sense. No, thank you very much, and thank you for answering my questions so well. Thank you.
Thank you, Bart.
Thank you, Dr. Pontieu. So now we are open for questions from the rest of the people. So, Lucas, are there anyone online?
No, if somebody wants to ask a question from online, please raise your hand. Zoom hand.
Yeah. In the meantime, we can take questions from the people here. So, Sanjit.
My question will be very naive. That when you are doing this fixed weather broadcasting, so I have two questions actually. So one will be the status with, let's say, the station L1 and so on. Suppose you always keep a satellite station in L1, and with all this machine learning to be continuous observing, will you be able to predict space weather like with pretty high accuracy in the next few years, or you will need some other breakthroughs in order to do that?
So if you actually look at all of these space weather forecasting algorithms that keep going on, they seem to hit some of a limit. So like if you look at it in terms of, let's say, cross correlation between the observed time series of incident measurement and the forecast, there's like a 0.7 is the best anybody can do. And there is like it seems like a ceiling that's there. You can go above 0.7 if you do some sort of thing, but these are not like, so if you play with the data set in a different way, you can generate better approximations. So if you take in, let's say, yesterday's solar wind measurement and give it to the model today, obviously the model knows what's going on. But if you give it just the changing conditions of the sun and ask it to forecast, there is always an upper ceiling or of some sort that is always reached. And that is I believe that is because of the fact that the solar wind is processed as it's coming from sun to earth. So if we can capture or quantify this processing in some way, we will be able to make better forecasts of space weather. So that is something I want to look at. Yeah.
But suppose like right now you are considering the image only.
Yes.
There are many other detectors on board in let's say and so on. Like looking at the magnetic field, the other particles and so on.
Yes.
So you combine those information, would you get better forecast?
Yes, that is true. The more data we have, the more better information, the more data we have, more towards the sun, and the more different kinds of messengers we have, the better our constraints will be on the solar wind models that we generate. The thing is, this model here right now can only forecast the solar wind speed, but then you can actually solve your equations, let's say your MHD equations, with constraints from all sorts of in situ and remote sensing measurements. And then you can generate the whole solar wind field itself. It's something that we can do. And the more set of measurements that we can, let's say from Aditya, from Papa or aspects, let's say, we can use that data, we can use part of solar probe data, we can use solar orbiter data, incorporate all of that and train your model in such a way that the more constraints you keep putting everywhere, the better your approximation of the solar wind flow itself is. And if you keep getting better forecasts.
I mean, you cannot say that before the spacecraft actually fly. Whether you are exceeding that 70%.
Yeah, so we can. I mean, so we can. The basic thing is we can have two sets of models: one which don't have the data and one which have the data, and then by and large compare them. How these compare. But incorporating any solar wind measurement much closer to the sun is going to improve the performance of any space weather forecasting model. That is something I can tell you.
Meaning, okay, my question was like this, that what you think? How do you figure out that which extra information?
Oh, like that. Okay.
In order to get the prediction very accurate.
Oh, if you can give me the velocities, let's say, velocities along the line of sight, let's say, from let's say the PSP or the solar orbiter, that will be a very strong constraint for what my model forecasts are, right? Because then you know what is happening on the sun, you know what the velocities are some place away from the sun and it's coming towards the earth. So that is going to give you a strong constraint on what forecast you can perform near the earth. So if you that's for velocity. For magnetic field, you need magnetic field measurements. For any other thing, let's say abundances, you need some abundance measurement. But abundance measurement will also need you to give a multi-wavelength data because you need to have a ratio of what sort of elements are there in various spectral lines. So yeah.
Awesome. Anyone to ask like when you summarize?
Yeah.
Okay. So again, this is a question coming from someone who's outside the field. If I look at the first sentence, impulsive heating is viable for heating the US photon. So when you say a sentence like this, it suggests to me that there are other possible viable explanations also. So my question is, what data would you require to really pin it down and say that this is the method that's happening?
So I have a very frank answer actually, and this is like a politically incorrect answer. So Von Neumann gave this very nice statement that you can give me 3 parameters, I can put an elephant. You can give me 4, I can make it wiggle its trunk. So you have a lot of models, and they give you. So you can. There are so many parameters in these different models that at some level you can actually tweak them to generate what kind of response that you're getting from the data. But typically, if you look at these wave-driven or impulsive heating, or let's say nanoflare paradigm, if you want to think of it like that, the time scales over which these different events occur, and the cross correlation of response across different temperature bands is something that has these two models are very specific signatures that one can possibly measure. And now we have gone to such an extent that we get very high cadence data, and predictions are sort of like within the cadence or within the spatial resolution. So it is not just like what. So we need to look at multiple wavelengths across the whole solar atmosphere to see if these different models can actually be disentangled properly. But these are all, so this is something which is a very statistical result, right? That's why I made this statement here. But you have very large events that occur all over the sun. And you can actually measure waves that are propagating outwards. You can see specules that are like jets, kind of like jets of plasmas, like going up and coming down. You can see that. You can see the plasmoids have been seen, for example, in the lower atmosphere. So large events you can actually sit and measure, but it is in the background in these very small, in very diffuse background where these constraints are not very strong.
My just to take it out one more quick question. So I can understand perhaps it's not like directly related to but the sun is supposed to be one among like a collection of star-1 main sequence stars.
Right.
So this is a very general question. Have people observed this coronal heating problem in other main sequence stars? So is it a general problem or is it something that so far only we have seen our sun?
You do see these highly ionized iron, for example, in various stars. So it is something that is observed in many other stars. And so there are also papers which assume sun as a star and then perform analysis to how you would estimate things from let's say other stars, because we don't resolve spatially in other stars, right? So we can do that also. So yeah. So only heating is there and it's there. I can't say for sure if it's there in all the stars, but at least main sequence stars, yeah, most of the stars, sun-like stars is there. Yes.
What research do you use for solar? What research? For measuring, directly measuring solar wave?
These are electrons.
It's
the particle measurement. So you basically have like you have these you have an electric field and you just reflect the electron and then you measure the energy of the electron, kinetic energy of the electron. You also have proton measurements and other ion measurements also.
When it's your separate.
So there's like a huge field that's there, and you have like a very small instrument that is collecting sampling some small part of the field. So what you're measuring is only a very small spatial location of the detector itself, and that's what we treat as solar wind measurement. But you're correct that it's a very large field that's displaying output.
And these like I actually don't know. It seems like the Parker is going to be closer to the sun measurement.
Yes.
The same
Yes.
measurement.
Yes. So what happens is Parker solar probe is goes much closer to the sun. So generally, all of the satellites are either Earth orbiting or sun orbiting. Parker solar probe has a very highly ecliptic orbit, so it goes very close to the sun and comes up. Because it goes so close, the temperature rises like very large. So it can sample all of these different measurements also, but the
These
instrument.
measurements you get as a special.
So we get particle measurements at different points in space as the probe is traveling. So we may not be looking at this. We're not sitting and collecting data. We're going through the space. So it is a bit more difficult to analyze that data. So they're not looking at the same structure, right? They're looking at very different structures as you're moving into the sun.
One quick question on this slide itself. So you firmly established impulsive heating is a viable mechanism. So in the community, again, coming from a person not in the field, what is the dominant accepted understanding? Is it the wave-driven heating?
So wave-driven heating can also be impulsive. So if the waves are dissipating very fast.
Impulsive heating is a viable. There are other alternatives, as you said. So what is the dominant understanding? Till now, it is all debatable.
Depending on which medium of the
Yes.
something.
So yeah, it's not a very correct answer I can give. Right?
Vishal said that you can resolve individual events where you can measure properties and compare them. But when you look at the quiet sun where everything is just a background, there it becomes much more challenging. Therefore, trying to quantify that. What
We can only say it is impulsive. We can't say if it is even reconnection driven or even wave dissipation kind of thing in this quiet sun heating case.
Could you talk more about the architectural CNN you use on the slides?
Sorry, will you come again?
In the PSM simulation, you use CNNs.
Right.
Could you talk about the architecture you use there?
You want the architecture? He wants to make me work hard. So, do you see the architecture somewhere? That's the architecture. It's basically a 1D CNN. You have this inception layer. I don't know if you're aware of inception layer. This was using RubyNet. So you have input here, you have an inception layer, you have multiple such convolutions, and finally a couple of fully connected layers, and that maps to your output. This is the model architecture. It's a 1D CNN. Okay. And we train this network using this loss function here. The two terms of the loss function. So if you know about smooth L1 or a loss like that, so that is the kind of loss that we have for training this network. So, and this is a set of parameters that we have. Yeah. This one or this one?
What is actually determines whether they are slope or like that?
So as the downflow velocity increases, so here magnesium K3, what happens is this region, so this thing is much down in the atmosphere. Okay, silicon forms much higher in the atmosphere, relatively. So model plasma is falling down in silicon, it's falling down in magnesium, and because you see that as the velocity of downflow increases down in the magnesium, that is also increasing in silicon. So that linear correlation is there. It's evident in this plot here. When I said that there is excess deceleration, what I meant was if you take a given velocity in magnesium, now let's say 4 kilometers per second, the velocity, the downflow is larger in Coixon and compared to Conover, right? Which means that velocity was larger, it came to 4. In Conover, the velocity was smaller, it came to 4. So deceleration is larger in Coixon when compared to Conover. So that's how you. So this basically is corrected from you take one pixel that in magnesium, you take the same pixel in let's say silicon. If both of them are showing downflows, you collect them and make the scatter plot. Bin them, get the scatter plot. Otherwise, if it's both outflows, you take that. You get this scatter plot. So on and so forth.
The outflows also have some kind of outflows also have some correlation.
Yes, yeah, they do. So that's exactly what the whole presentation is about.
We have some time constraints, so we will to conclude the session very soon. I suggest to people who have questions, they can have a discussion with Vishal after this talk. I think Vishal has done, as we all see, very exciting work. He has produced very interesting and important results, and he has now also completed all the formalities for the award of the PhD degree. So let me confirm from the external examiners if you can refer Vishal as Dr. Vishal officially. So Dr. Harra and Dr. Pontieu, can you please tell us?
This is clapping and
Yeah, I'm clapping too. Yes, congratulations.
Congratulations, Vishal. It's really impressive work. And I wish you luck in your new job. And hopefully we'll collaborate in the future, I'm sure.
Absolutely, yes. Looking forward.
Many congratulations.
Thank you.
Thank you. So we call Vishal as Dr. Vishal now, and thank you, Dr. Harra and Dr. Pontieu. You may leave now.
We will
Louise and Bart. So there is one form that needs to be signed. I will fill that up and I'll send it to you both, and we can sign and then submit it.
Okay, perfect. And
Sounds good.
have a good
celebration. Thanks, Bart.
Thank
Yeah,
you.
thank you, and enjoy the celebration. Yeah.
All right. Thank you. Bye-bye.
Bye-bye.
Oh, you got it done.
Yeah.
Aha. Hey, Vishal, so this is for you.
Oh, thank you. Oh my God. Thank you. Like, yeah, that's nice. Cute.
It's a long story for that. I'll tell you.
Right? You should come here. Come on, come on. You should come here.
Yeah,
You come. Yeah, yeah.
Thank you. Yeah. Yeah, it is there.
वो है ना उसकी बिना कैसे Yeah. Excellent. Congratulations. Thank you.